Okay, so one of the things that we have argued is that position is not an observable. So it's good to learn when things are not an observable. That's some extra knowledge. But we should also learn what is observable in a relativistic quantum theory. So what are natural observables in a quantum field theory? And to sort of think about what observables are allowed, we're going to start asking ourselves, our theory has to be consistent with special relativity. Well, how does that constrain the possible observables we could have? And our theory must also be consistent with quantum mechanics. How does that constrain the possible observables that we could have? So let's start off and let's consider the constraints that come from special relativity. If we understand these constraints clearly, and we understand the constraints that come from quantum mechanics clearly, then we'll know what constraints in a relativistic quantum theory, we'll know what constraints there are on observables in a relativistic quantum theory, and this should suggest to us what observables we can have. So in special relativity, the basic constraint is that you can't move faster than light. So you can't move faster than light. So let's see why this leads to some constraints on what we can measure. So to start off, let me just remind you of something. So I'm going to draw a space-time diagram. Here is t, here is x. On the space-time diagram, I want to draw a line. So here it is, 45 degrees. This would be the world line of a pulse of light. And of course, I'm using units where c is equal to 1. And let's imagine that this is where you are. So that dot over there, that is you. Okay. Now, let's consider this point over here, A. Okay. And we're going to consider this point over here, which is B. So I would claim that you can never get to B. So I claim you can never get to B. Let's see why. So to get to B, this is how far you have to move. So you have to travel that distance. In what time do you have to do it? Well, you have to do it in this time over here. But in this time here, look at the pulse of light. How far could light travel? Well, a pulse of light released from you would only get to this position over here. So if you're going to get all the way here in the same amount of time, you're going to have to travel further than light can possibly travel. So to get to B, you are going to have to move faster than light. Okay? So that's why I say you can never get to B. Okay? So the basic point is to get to B, you will have to move faster than light. I also claim you can get to A. And it's very similar logic. So let's just go through this and try to understand it. So to get to A, that's the distance you have to travel. So you have to move that far. And what time do you have to do it in? Well, you can do it in this amount of time. How far could light travel in the same amount of time? Well, here's the world line of light. So in the same amount of time, starting from where you are, that's how far light would get. So light would get further than you get. So if you're going to get to A, you only have to move slower than the speed of light. So you're not breaking any law of physics to get to A. You're not having to move faster than light. Okay, so good. So you can get to A, but you can never get to B. So I think we've discussed things like this, very similar to this before. So now let's see why this will affect what observables we can have. Okay, so remember, in fact, let's leave that there. You can never get to B, but you can get to A. Now, let's imagine that I ask you a question, okay? So I have built a light emitting diode, an LED. So I have built a light emitting diode. Let's say it will flash green or blue. And it will flash at a specific time. Okay. And then I ask you a question. Will you measure? So will you observe the color? And I want you to tell me, is it green or blue? Okay, that's all I want you to do. Now, in order for you to do that, you have to ask me some questions. And the reason why you have to ask me questions is the following. Let's imagine that this line over here is the light emitting diode. So this is the world line of the light emitting diode. Okay, so that's the diode as time goes by. And let's imagine that this is when it will flash. This is the time that it flashes. So let's call this T flash. Now, if that's the case, and you're at the red dot, then to measure what color the flash is, you have to move to B. But we've already said you can never get to B. So if that's the world line of the light emitting diode, and this is the time of the flash, you have to apologize and tell me you can't make the measurement because it's physically impossible for you to make the measurement. You can never get to B. Okay? On the other hand, let's imagine a different scenario. So now let's imagine that the light emitting diode, this was the world line of the light emitting diode. So this is the LED world line. And now let's imagine that it's going to flash at this time. Well, what that means is for you to make the measurement, you have to get to A. And you can get to A. You don't have to break any laws of physics to do that. So this time, you would be able to make the measurement. So to decide whether you can make the measurement or not, you have to know when you have to measure and where you have to measure. Okay? So this is now a very important point. So let's just summarize that. Super important point. To decide if you can make the measurement or not, you need to know when you must measure and where you must measure. Let's just draw the space-time diagram again to bring one point home. So this is X, this is T, that's U. Let's draw in, exactly here we had this blue line. Let's draw in the world lines of light. Okay, so here's a pulse moving to the right, and here is a pulse moving to the left. You are able to get to any point inside this region. That's called the future. your future. So you can measure anything in your future. If there are people in your past, this is your past, they can get to you and they can communicate with you. Okay? So you can get to any point in your future. Anyone in your past can get to you. This red point is called your present. That's right now, that's your present. And this yellow region over here, this is not past of your past or your future or your present. This is called the elsewhere. You can never measure anything in your elsewhere. You can never get to points in your elsewhere to make measurements. And that means that a given person in the universe cannot know everything. They can only know what is in their own future. So it is not possible for someone to know everything. You can only know what is in your future. To decide whether you can know something or not, you're observable. Okay, let's call it O. To decide whether you can measure this or not, you need to know when you must measure. So you need to know the time of the measurement, and you need to know where you must measure. So you need to know the position of the measurement. Okay, we will continue in a minute.